for it. So long as you take it, so it's easy. Right, it's defined, but
the circuits for those into the classifier.
right, that makes sense. They don't have a separate. In our, the way we were thinking about functions, there's two hypothesis classes, one defined, so essentially see this?
Yeah.
Of course, you only need complexity for the first things you're learning as production groups. But yeah, I can understand the.
So, when we get a chance, let's talk a little bit more about essentially two roles. One role is to define the groups, but the other role is to define the things that are significant features that give you information
Right.
for creating
Their
the
concept classes like linear combinations with the group functions.
right, or noticing that being able to run this distance from this age corresponds to whatever.
Yeah.
And that's and they don't distinguish between them. And I don't know how to do it. It's an interesting general question.
Yeah.
Whether you can split these apart. But it's some kind of just
That makes sense.
yeah.
Okay, great. So thanks for inviting me to talk. And I'll be picking up basically where Guy left off, talking about some recent work we have on evidence-based rankings. It follows in the multi-group fairness perspective. And this represents joint work with Cynthia Dwork, Omar Reingold, Guy Rothblum, and Gail Yona. And it will appear at Fox this year. So the motivation for this talk is that often ranking is sort of the underlying motivation for prediction. So for instance, you can imagine Cal Berkeley is running college admissions, and maybe when applicants come in, they'll predict some probability, say the probability of graduation within the next 4 years. And then after developing some prediction, they'll select the top K applicants based on this estimated probability. So this is a way in which the prediction task is really just a means at getting at some underlying ranking. Ranking is also at the heart of a number of alternatives to affirmative action. So for instance, in Texas, the top 10% rule was enacted basically as an explicit alternative to affirmative action, where the top 10% of the graduating classes in Texas are automatically accepted to state-funded public universities. I think, yeah, some form of this is also true in California. But the point is that somehow you need to rank individuals before you can even hope to do something like this. So the concrete task that we'll have in mind is to try to learn to rank individuals by some probability of outcome, where again we'll refer to this P star, this probability of an outcome given an individual or the features of an individual. And so for concreteness, you can think of this probability as being the probability of graduation within 4 years, or in a very different setting, maybe the probability of needing medical attention in the next hour. So for medical triage or, wide variety of applications. But the challenge is that typically we don't observe probabilities in the real world. What we observe are outcomes. So, we might have access to a rich set of features about an individual, but oftentimes we can't, say, resample from this distribution or this probability distribution over outcomes. So for instance, when we say we might have access to, did the person X graduate college in 4 years, we can't then go back and say, try a different college, run for another 4 years and see how you do again, 1 over epsilon squared times, and now we have some estimate of P star. No, this is more subtle. We have access to sort of binary outcomes, 0, 1 outcomes, say of you did graduate or you didn't, and now we want to go back and sort of estimate and hope to rank people based on this underlying probability without direct access to it. So for instance, it's not sort of this setting is subtle and challenging for a number of reasons, but one concrete reason is you can imagine flipping two coins with different biases. And just look at the single outcomes based on of these two coin flips. Comparing the coin flips tells you very little about sort of how to compare the underlying probabilities or the underlying original biases.
I can't stop myself, but what's the definition of this P star? I mean, you know this famous article, what's the probability that there will be an earthquake in San Francisco in the next 30 years?
Yeah. So for now, just think of it as the probability of outcome given the features that you observe in some underlying data distribution. It's just the Bayes risk, say.
Michael, this example actually is a good example of the fact that even here it's not really a binary thing. So in other words, you don't really want to know whether they graduate in 4 years or not. You want to know what is the expected length of how much time, you want to know how much time they're going to take. Right? So if you could give somebody a score according to how much time they're going to take, then you would rank them according to that, and for some reason you want them to graduate quickly, then you take the people who less.
You can get that from us.
No, you can, but if that was your goal to begin with, I'm not sure.
Right, so
It's the same
Not
kind
much
of
about
algorithm.
graduation,
What?
just want to, this is just.
no, I agree, and so this is sort of a question of like limited or bad proxy, right? Like really what we want to predict is like your probability of success or quality membership in the Cal Berkeley undergraduate community. But
This is closer. Time, equality, that's too...
yeah.
No, because remember there was the talk of Stanford, the economist, in the first workshop?
Maybe, yes.
Anyway, but he made that point very much about how much cost in a health system.
Right.
Ranking according to cost, he said if you would rank them across versus the benefit, the health outcome, you would have a completely different...
I agree. Right. So certainly the outcome or the outcome that you choose to predict the probability of, it matters immensely. And so for the sake of this talk, we'll assume that sort of we all agree on what the outcome is. But I think it's a great point that there's subtlety even in determining what the task is and what we want to rank according to. So as we've been saying, the goal will be to learn to rank individuals according to some probability of success without observing these probabilities directly, only observing outcomes. And we'll be concerned with notions of accuracy as well as fairness. And we'll touch on these as we go along. So before I do anything else, I want to suggest that ranking is a more subtle task than prediction itself. So as we talked about, the first idea you might have is to learn a predictor and then rank individuals according to the predictor that you've learned. And we'll see that even if you're able to very precisely recover an approximation to this underlying risk, P star, it gives you very little guarantees about the ranking that you might produce. So let's consider the following toy example. Suppose that in our population S and T, P star is distributed, there's two populations, S and T, and the risk is distributed as P star of X in S is 1.0, they're all going to be positive outcomes, and in T, it's much lower, 0.1. And suppose that in our predictor that we learn, we even get all of T correct. We get it precisely, we learn some P that is, perfectly predicts the individuals in T. But in S, we do a very poor job. We predict them completely wrong. We predict them 0.0. But now the point is that if S, has probability mass less than or equal to epsilon, then the predictor on the right will be epsilon close to the predictor on the left. That's to say that we basically any epsilon accurate predictor can sort of rank in the induced ranking can rank them arbitrarily, a group of size epsilon. So one thing to note here is that this kind of transposition could be viewed as mistreatment both for S and for T, even though we've learned perfectly in the group T. So for instance, if we were trying to predict, depending on your task, basically being at the top of the rank or the bottom of the rank might be good or bad. So essentially, the point here to observe is that somehow ranking feels like a much more global task than prediction. In other words, mispredicting in S or in some small group might actually affect the ranking of some much larger group, even if you understood that group very well. So, as my talk suggested, I'm going to talk about evidence-based rankings, and I'll go through some setup as well as sort of our first notions of some notion of fairness, even when you can't maybe recover the ranking exactly. So let's go through some of the setup first. So as before, we'll have, as is standard in prediction, we'll have a distribution over individuals as well as a distribution over outcomes, where the outcomes are sampled according to Bernoulli of this P star. And we receive labeled samples, and a small number of them. We hope to learn some ranking now that will generalize. And ideally, we would learn something that's close to the true ranking. And even if this is not attainable, we want to have some guarantee over the way that our ranking ranks different groups of individuals. So again, the challenge here is that we don't have direct access to this P star. If we had direct access to this P star, then we could hope to implement sort of a comparison oracle or something of this nature and exploit techniques there. Yeah?
Sorry, P star is a vector, and it's the Bernoulli parameter for each individual in the data.
That's right.
Okay.
Mm-hmm. So while this setting is challenging, again, one thing that we could hope to do from a small sample is estimate statistical queries. In particular, because of the way that we assume outcomes are distributed based on P star, we can assume that for a fixed collection of subsets, for each of which are sufficiently large in our distribution, that we can get our hands on accurate estimations of this expected value of P star in the subset based on the empirical expectations of Y in our set, in our training set. So in other words, this, if we had a class C of statistical queries,
It's enough it's a fixed S, or you want to do it uniformly over a collection of S's?
we'll think of it over a collection. So right, so for a collection C of statistical queries, we can hope to, from a small sample, get a uniform convergence bound and say that with high probability, our estimates in the sample will reflect that of the true underlying risk, and that this class of tests provides reliable evidence and ways to reason about the rankings, even without direct access to P star. So there's been a lot of prior work on ranking individuals and learning to rank. But often, almost all of these works assume some sort of comparison oracle or some sort of access to this underlying P star or the underlying sort of ranking itself. I think our work maybe is most similarly motivated to the work of Kearns, Roth, and Wu. And having talked with Stephen a little bit about it, I think our work maybe sits sort of before their work in the pipeline, where we're trying to estimate somehow these the ranking, and then once you do that, you maybe can do interesting notions of affirmative action or cross-selection. So just some there's a tight connection between ranking and prediction, and we'll see some of that here. So one thing that we have been alluding to is that every predictor induces some sort of ranking. So if I lined the individuals up based on their probability or their predicted probability, I can map those into a ranking. And I can do that formally. I don't think it's too important for this talk. And we have some convention that the smallest individual in the ranking is the best according to P. Similarly, every ranking has a family of consistent predictors. So in particular, if I was given a ranking, I can then map them into some plausible predictor based on the rank that I've been given. And this should be monotonic. It should allow for ties, but not for crossings. So for instance, this is one consistent predictor, but this could be a very different one, right? That maps individuals to different probabilities. So I'm going to get further into some of our notions of fairness now and revisit this original example of that we had to start that motivated us. So the main concern that we have with this sort of issue of ranking when approximate recovery isn't enough to guarantee recovery of a ranking is that somehow our ranking would consistently undervalue certain subsets over others. So for instance, recall that this was somehow the original ranking according to P star, but our estimated ranking sort of transposed these groups. And what happened here? What feels objectionable about this ranking is that we had a set S whose outcome probability, the expected outcome probability, was significantly larger than that of T's. You know, P star here is, the expected P star is 1 versus 0.1, but yet the ranking favored T over S, sort of universally. And so this is a type of inaccuracy in the ranking that feels blatantly inconsistent with not only with sort of what we feel is good, but is blatantly inconsistent with the evidence at hand. So in particular, if we were able to identify this group S and T a priori, and we could measure a statistical query on each of these groups, then this ranking blatantly violates the evidence in these groups. So to be a little bit more formal about what I mean by the ranking favors one group or another, we have this notion of domination. And so the formal notion isn't too important, but you can think of it as saying that there's that one group dominates another, that S dominates T if there's like a downward matching from T into S, such that all of the in the matching, all of the individuals in T are ranked better than their counterparts in S. And we can generalize this to sets of different cardinality. So this leads us, sorry, is this notion of domination clear?
So the ranking is ground truth, or the ranking is, you assume that there is some ground truth ranking when you define this notion. What is this R?
No, sorry. I'm saying that T dominates S within a ranking. So parameterized by a ranking, given a ranking, then T dominates S within this ranking if there's this downward matching. Good. So this leads us to a natural notion of domination compatibility. So we say that sort of informally, if the probability of success is higher in S than in T, then T should not dominate S in the ranking. Right, so going back here, this was precisely the problem that happened in this setting, where the expectation in S is significantly larger than in T, but T dominates S in the ranking. So this is our first attempt at preventing such transpositions. And again, we won't just want to apply this for a constant number of sets or a set of sort of protected groups, but we'll try to apply the multi-group perspective and enforce this notion for a rich class of groups, defined possibly by a computational class. So the formal notion is that a ranking R is C domination compatible if for all pairs of sets S and T from this class C, if T dominates S, then sort of the expectations match. The expectation of T is at least that of S. Yeah?
Are you going to get any weirdness coming from the fact that T no longer dominates S if S has like one outlier that's higher than...
Great, that's a fantastic question. So we'll, in how I've presented it here, yes, but we handle this kind of approximate domination in the paper. So it's not an issue, but it's a great question.
So what is the definition of domination when the sets are very different size?
Yep. So it's another great question, and you. So yeah, the question is what's the notion of domination when the sets have very different cardinalities, and it's a great question. It's a little bit technical, but you can imagine drawing sort of a vertical line here and thinking about this matching as defining some sort of crossing or talking about sort of where individuals are relative to the vertical bar, and it's technical, but it's not. It makes sense once you. I don't want to get into it. We can talk about it offline if you want. And yes, again, sort of our formal notions that we work with in the paper allow for additive approximations here and handle this approximate domination as well. Good. So why did we feel like domination compatibility is a good idea? Well, so these violations to domination compatibility feel objectionable in the sense that it feels like there isn't a consistent predictor underlying this ranking that respects the evidence given by our class C. And in fact, we can prove a lemma that sort of exactly says this. So the lemma says that suppose T dominates S in R. If a predictor is consistent with this ranking R, then the expectation of P in T has to be at least that in S. So that's to say that if R is not C domination compatible, if this ranking isn't compatible in this way, then there is no consistent predictor that respects the tests given by C. In other words, this ranking cannot be the true ranking. Right? Because we assume that this true ranking arose from P star, which is a consistent, which is a predictor that's consistent with the true ranking. So this is one justification for why domination compatibility makes sense, but sort of we have this objection that there isn't a consistent predictor that respects the evidence given by C. We could go a step further and actually require that there be a consistent predictor. And this would be some sort of strengthening of this notion. So this motivates a new notion that says a ranking is good if there exists a predictor that does respect the evidence given by C that's consistent with the ranking. And this is exactly our next notion, which is evidence consistency. And so formally what we say is that a ranking R is C evidence consistent if there exists a consistent predictor P such that for all sets in our class C, the expectation of P under S is equal to that of P star. That's to say that it's respecting the evidence in the data. So some properties. Evidence consistency implies domination compatibility. And this is basically direct from the lemma on the previous slide. And further, this notion of accuracy on the empirical or on the expectations given by C is exactly the notion that Guy just presented of C multi-accuracy. So another way to say this is that a ranking is C evidence consistent if there exists a consistent C multi-accurate predictor. So it feels like a much stronger condition than just this domination compatibility, in that we're requiring that the ranking actually respects some the ordering of some predictor that is somehow globally consistent with the evidence at hand. Right, so that gets into this interpretation. That in some sense, this globally consistent predictor, this multi-accurate predictor, is what justifies this ranking. So any questions at this point about this definition? Okay, so
I want to say that if instead of exist a consistent predictor, if P star is consistent with respect to R.
right, so again, this would be the ideal. This is what we would love to get our hands on, and it might not be sort of either computationally or statistically feasible. And so this is somehow our best way into that, right? That if all we have are these statistical tests, then we can't hope to say that on an individual level that we're consistent, but at least on these large groups that we can audit, we're consistent. So sort of mapping out these various notions. I know that there's a lot of them, but we can sort of see what in the predictor world we had this notion of multi-accuracy, and it's very tightly connected to this notion of evidence consistency, which we said implied this intuitive semantic notion of domination compatibility in the ranking world. So then we turn to the question of actually learning such a ranking. How do we get our hands on one of these things? Well, we can reduce learning a ranking to learning a predictor, as we wanted to in the first place. But now we can do it in a way that we get some guarantees over these groups. So in particular, the induced ranking of a multi-accurate predictor will be evidence consistent almost immediately based on the definition and the connection to multi-accuracy, and thus will also be domination compatible. And as Guy talked about, we have a learning algorithm for multi-accuracy, and we can reduce this problem to learning over C. Yeah?
Just for my intuition, is there a simple example of like what a ranking would look like that was domination compatible but not evidence consistent?
It's impossible. Yeah. So evidence consistency implies domination compatibility.
But how about the other way
Yeah.
around?
Oh, sorry. So you want something that is evidence consistent but not domination?
Other way, I thought. Domination compatible.
It's not bidirectional, it's strict.
Yeah,
So
Right.
it's once an example.
Yeah, is there like a simple example of how you can satisfy one and not the other? Or
It's a good question. Gal, do you have?
One example, but none of the authors.
No. So actually, this is something that we struggled with for a while. But you can actually, so in our paper, you can see, whatever section it's in, and actually, we can construct instances where the tests will sort of be locally consistent, but not have this global consistency in a way that actually demonstrates the fact that domination compatibility is actually a strictly weaker notion. We can prove that.
And there is an example in the paper.
Yeah.
I
It's just don't, it's not easy.
But it's subtle, and it wasn't a priori clear. Initially, we thought these notions might be equivalent.
Do you have any example where ranking doesn't go through prediction?
It's a good question. We reduce it to the problem of prediction, but so especially because of our model of access to the data, I think this is very natural. We're only getting to see outcomes of individuals. So in a sense, our information is about is statistical information about the outcomes of individuals. So it's very natural to then try to learn something that is consistent with a predictor and then turn it into a ranking. In other models where you get access to these comparison queries of is x better than x prime, it's much more natural to rank directly. Yeah?
comment and a question. So the first comment is you said for learning to rank that there's, we're talking about related work, that there's not that much of it that deals with this kind of binary outcomes. But there's actually a lot of it that deals with binary outcomes. Like anything that, there's a ton of work in that area on clicks. And so a click is, a binary outcome. And so you're just trying to predict what's the probability someone's going to click on something, but all you actually have are clicks or no clicks. And so that,
I see. Okay,
it's
good.
the same type of thing, learning to rank there, where you want to predict for that and make sure that you're putting people that are, if you had to rank people who you're going to show or show what
Good.
which website you're going to show.
Good. So it is learning to rank in the setting of a binary outcome, but it's also going through this reduction to prediction.
Exactly. So
Okay,
it works the same type of way. You build a predictor and then rank based on that.
Yeah, I'd love to get those references.
And then the question is, just like this is a holdover from the first talk, is there some sort of objective that you can say you're doing gradient descent in here for this algorithm?
So for the multi-accuracy and multi-calibration, in some ways, yes.
I mean, for the ranking.
For the ranking, it's not. I think I'd have to. It's not obvious to me.
You need a notion of loss, and then you
Right.
value descent on the
Right.
loss.
Yeah.
But there's a lot of ranking losses, right, that take into account where
Right.
the ranking.
And yeah. So I don't think our notion is directly related to any of them. I think, in a sense.
You can think of the domination compatibility as kind of naturally defining a loss function, right? As long
And it sort of generalizes from these individual pairwise notions to a group version of it.
So by the way, for the click prediction, can you clarify, is it in fact ranking or is it above threshold? My recollection when I last saw this stuff in real life in 2014, it was above threshold. So if the probability was above a certain amount, then...
Well, you do all kinds of things with it's the same type of thing where you build a predictor and then rank things. And then you could either choose top K or actually produce a ranking. It's kind of what happens at the outcome is another question. But there actually is something where the data is binary.
When I saw this in Bing, it was predict the probabilities, and if it was above a certain threshold, then they were candidates for the ad.
I see. So yeah, but I think even just on URLs,
As opposed to ranking.
you're going to think of URLs for a query and rank all the URLs for a
I
given
see.
query. So
Good,
you're going to produce
thanks.
a ranking.
Great, thanks. Yeah, so happy to take it offline. So now with these, with our sort of landscape of various notions of ranking fairness conditions and a way to learn rankings that satisfy these conditions, it's natural to ask, are we done yet? Or are we there yet? What we'd like to say now is that actually, even though we get these strong properties of no transpositions in these groups defined by this class C, maybe we're not done. In particular, we're going to look at the weaknesses of these predefined statistical tests and see that actually there's a number of desiderata that we might ask for that are not yet satisfied. So in particular, let's try to poke at evidence consistency and see how we can abuse it. So suppose that our reality was over on the left, where P star in our population S is about 0.8, and in T it's about 0.5. And this is uniform across the groups. Now I want to come up with a ranking where some amount of T dominates S. And I want to do this because I'm malicious. But I note that my expectation of P star is only 0.5, and the expectation of P star in S is significantly larger than that. So using P star, I'm going to have difficulty. In particular, this set that I've called T1 and S, they violate the domination compatibility. And so this wouldn't be evidence consistent. But P star isn't the only predictor we're allowed to use. Recall that the definition of evidence consistency said that there must exist a predictor that's consistent with the ranking that respects the evidence. And so the question is, does there exist one? And in fact, there does. We can choose some predictor P and assign the individuals in T1 to be 1 and assign the individuals in T0 to be 0. And note that the expectation of this P is equal to the expectation of P star on this set T. So even though this feels somehow like we're blatantly abusing this ranking and ranking some group over this other group S that is more qualified, the ranking satisfies evidence consistency with respect to these groups S and T. What we would love is to somehow provide some guarantees with respect to T1 and T0 and S. But the problem is that T1 and T0 were not included in our class C. In fact, they're only defined after the fact. They're only defined by the ranking in question. A priori, we had no notion of a T1 and T0. There's no T1 and T0 on the left. So somehow we have to augment our understanding of what is a reasonable class, what is a reasonable statistical query we can ask in order to hope to guarantee prevent this kind of domination incompatibility. Yep.
So is your predictor no longer deterministic?
No, this predictor could be deterministic.
In that case, why would you get, for the same x, are these different sets?
You can imagine they're different x's, yeah. That there's many individuals within T.
But if they're different x's, then T1 and T0 are now defined by something other than the ranking, right?
No. The T is a subset that's defined by, say, the first attribute in X, and only depends on the first attribute. And
but like if you're saying that T1 and T0 are different on some other attribute, right?
no, not necessarily. Yeah, I mean, I guess so. But the point is that according to the tests that we've defined, this class C, which we're taking just to be the class S and T, this is all that our notion of rankings know about. This is the only evidence that it has access to.
C is a collection of sets. It doesn't include T1 and T2. It only includes
Aaron, and then Rich.
Yes, so taking the sort of like complexity perspective of like C, so your like algorithms for learning multi-accurate predictors will learn a circuit that's only like slightly more complicated than C. Mm-hmm. So if you, like, wouldn't this problem be solved just by taking as your class C the slightly larger set that...
So I want to argue that this isn't just an issue with like adversarial manipulation. So consider the following scenario where S has expectation 0.75 and T has expectation 0.5. Then a very reasonable thing to do that I think our multi-accuracy algorithm would basically do is use some max entropy predictor. And if you don't know what that means, don't worry about it. But it's a very natural idea of how to predict. And in this ranking, according to this predictor, S would be ranked above S intersect T above T. But in fact, the true underlying probabilities might be that S has, S minus T is 0.5, the intersection is 1.0, and in T minus S, it's 0. So the true ranking would have S intersect T above S above T. So in fact, there's no way to certify this without looking at this intersection. That again was only defined a posteriori, after you specified the ranking.
So this seems analogous to multi-calibration though, right? Because calibration is all defined based on the predictor, not on...
We're doing great, yeah. So we'll see that there's actually a very tight connection to multi-calibration. So in some sense, what we want to do is we want to incorporate information about our current predictions in order to inform our statistical queries that we make, right? And so in a predictor, we can look at the level sets. That's sort of the notion of statistical tests that will look at the individuals in a certain prediction range. In a ranking, we can look at the quantiles. So in particular, there's this idea that rankings, once you have them in your hands, they define important sets. For instance, you can think of the individuals who are ranked in the top 10% of the ranking. And these sets actually interact in very interesting ways with the sets in your statistical tests. So in particular, you could ask for the individuals ranked in the 40th to 50th percentile who are also in S, a set in your predefined class of tests. And so this is basically some technical way of saying that we can define new statistical tests that say, I want the expectation of S of P star, or expectation of P star in S conditioned on the fact that your rank is in the range T right now. And so in particular, because these quantiles, these sets that were defined by the ranking, violate domination compatibility, this will not satisfy some stronger notion. So we define a series of reflexive evidence-based rankings based on domination compatibility and evidence consistency. And where we're taking expectations now, we're investigating our rankings based on the statistical tests that we defined up front, but also the current ranking. We're letting our statistical queries depend on the ranking in question. And so as before, this stronger notion of evidence consistency implies domination compatibility over this class of tests. But the surprising thing is that the reverse implication also holds in this stronger setting. That's to say that if a ranking is CR domination compatible, it's CR domination compatible if and only if it is CR evidence consistent. So in other words, once we allow our class of statistical queries to depend on the ranking that we have in our hands, these notions are equivalent. So it reveals some surprising strength of this semantic notion of domination compatibility. So when the sets that we query are allowed to depend on the ranking in question, then domination compatibility implies some notion of global consistency. And as I mentioned earlier, it actually does require this notion of self-reference. Like the regular vanilla C domination compatibility is a strictly weaker notion than C evidence consistency. So as Rich is getting at, like again, we have this very natural, feels very familiar to this idea that we had in multi-calibration, where we're defining statistical queries based on our prior queries and based on the ranking in our hands. And so we also proved some very tight connections between evidence consistency in this stronger setting and multi-calibration. So the theorem is that basically these notions are equivalent as well. So our picture before was that we had this predefined class C, and we had some implications. And once we allow our tests to depend on the ranking in question, all of these notions are essentially the same. So I'll just finish with saying that this actually gives us some interesting perspective on properties that you get from multi-calibrated predictors. In particular, if you use a multi-calibrated predictor for ranking, then you get these non-transposition properties basically for free. And it strongly suggests that this idea of multi-calibration really encourages this global learning across all populations. So I'm done. Thanks.
Take
Yeah,
a couple
sure.
questions. Yeah, so unless you really go over all subsets, you could see all subsets, and you use a C, you come up with a ranking R. Now you have a new collection, which are the R related, and now you have to learn again and come up with a new R star, and this may never converge. Unless you are doing multi-calibration with respect to all possible subsets.
No. So one thing that I didn't include in any of my slides was an additive alpha slack factor. So once you allow yourself some slack and you just require that you get within this alpha ball of sort of calibration with respect to P star, then like these issues of convergence go, like you will converge with an appropriate step size. And again, it follows by some sort of gradient descent style argument. Happy to talk about it offline.
Questions? All right, let's thank Guy and Michael again.